All right, so another way to categorize machine learning systems is whether they're batch or online learning. In batch learning, you have to train it using all the training data all at once, and then it's learned, and then you just use it. So it's trained offline and then run in production without any more learning. And this is how Google Bard and ChatGPT are. They've learned on data up to a certain time, I think 2021, and they don't learn anything more after that. So this means the performance will decay. Now, technically, the performance remains the same, of course. It's not changing, but its ability to succeed against real modern data will decay because the modern data will keep changing, and the model will get more and more out of date, no longer not knowing whatever the latest new innovations are. They can call that model rot or data drift. So the solution to that is that you'd have to periodically retrain the model with up-to-date data. Now, in online learning, you train the system incrementally, so you can add new training data to it periodically, and then you can follow something like stock prices. You can also work with weak devices like cell phones because the training doesn't involve so much data all at once. You might also do this if you have a huge data set that you can't fit in main memory all at once. If I collected some gigs of Reddit discussions, no human marks and tags, can I train something? Yes, exactly, Zhu, and that is exactly how ChatGPT and Google Bard were made. They trained it on just a vast amount of data from the internet with no tags. And what it did was find patterns in the language. So it learned the structure of the English language by just analyzing vast amounts of unlabeled English. That's what it did. It did not learn to sort it into categories or anything like that. And that's why we end up with the current situation where things like Google Bard and ChatGPT can write paragraphs and pages of text that looks pretty good and answer questions, but they can't tell good things from bad things. You can't tell them, don't tell people to do something illegal. Don't tell something disinformation, because they didn't learn any of that, because none of the data they took was labeled. This is disinformation, this is accurate, this is inaccurate. So they've learned to make English look good, but they don't have any way to label it in useful labels now to deal with the security consequences. Yeah, I know large data sets have human marks and tags. Some of them do, but I do not think the large language models came that way. However, that's my understanding, although I'm not an expert in it. There may be more to it that I don't know yet. Anyway, so then, so if the model learns quickly and keeps learning on new data, then that will mean it will forget the old data, right? If it's learning like what pictures, like a man versus a woman, it's learning to sort them into men and women, and then all the women start wearing different clothes and hairstyles that look very different. It might learn the new hairstyle for the new pictures, but that means it'll be less accurate on the old ones, that sort of thing. Now, another issue is generalization. You train your model on training data, then you give it a new data it's never seen before, and how accurate is it? That's called generalizing. Can it take what it learned from the training data and successfully generalize that to make good conclusions about the new data? Now, instance-based learning is one way. It memorizes all the training data, and now whenever it sees a new thing, it calculates how close it is to the existing one. So you have something like this. It's memorized all these. You have a new one. It says, well, it's close to this triangle. I called it in triangle, close to this one, and close to this one. So I'm going to call it a triangle because it's closer to the triangle categories than the squares. So it works by just memorizing all the input data and then having some way to calculate the similarity of new data to the known data sets. That's one way to do it. The more common way to do it, and the way I think about it, like nearest neighbor classification, And but the more common way, which I think of because I started in science, this is what scientists do. Scientists don't just memorize a bunch of data points and then compare new data points to the old data points. They create a model which will be mathematical and say, all right, here's the curve. Everything on this side of the curve is a triangle, and everything outside that is a square. This is what scientists do. They'll develop a model with a mathematical barrier, mathematical criteria, and that's what's used to predict it. So that's the other way to do it. So for example, if you wanted to determine whether money makes people happier, Well, you could download the GDP per capita. Is available, easily available online, GDP per capita of various nations, and you can also download the life satisfaction score on a scale from 1 to 10 or something of people, and then you can combine those two and make data that looks like this. So if you do that for some data, you get some GDP per capita between like $30,000 and $60,000 here. And so you see, if you just take a quick look at it, the people on here are kind of low, people here are higher. So there does seem to be some trend that more money makes you happier. So you might think it'd be good enough to just put a straight line through this data. So if you're going to do that, then you have two parameters, slope and intercept, which for some ungodly reason your book called theta 0 and theta 1 instead of using mx plus b like every simple math book I ever did. But anyway, the point is now you can have all these different lines. The line with a slope of 0, negative slope, positive slope. So you want to find the best fit. So the way you do it is you have to have either a utility function, which gets large when the model is a good fit, or a cost function, which gets large when it's a bad fit. The one I typically used was calculating the squared error. You take the vertical distance between a line and every point and square it and add it up. That would give you a cost function that gets big if you're far off. And then you can find the line that is the best by one of these measures, and there's an example of a line that fits this best. So that's one way to do it. That's regression. So here's some challenges of machine learning. One common problem is you don't have enough training data. This is why in the current situation there's a huge legal problem, because the people that want these models are doing stuff like just scraping Facebook to get images and scraping the internet to get text, and they're taking a whole bunch of data that isn't really theirs. And then when they use it, then they're getting copyright infringement lawsuits saying, wait, you didn't really have the right to use that data. And that's a problem. They didn't have enough data that they had direct ownership of, so they start taking other data because they need more. You can also get data that doesn't really represent the class. So you train on it, but when you try to generalize to real images, they are not really the same. Poor quality data, data that doesn't have the information you need, data that has irrelevant information that just gets in your way. And then there's overfitting and underfitting, which we'll talk about. So one thing to know is that it turns out that the type of model you use is not as important as the amount of data. There was a test that showed that really if you just have a large amount of data, then almost any model will work. So that's a good thing to know. It's not so much choosing the quality of your model. The most important thing is finding enough good data. All right, now here's non-representative training data. When we tried to predict happiness of nations, this was the blue dots are what we had before, but those only had a limited range of income from $30,000 to $60,000. If you include more data from other nations, you discover there are some nations that are much poorer, and yet they seem to be mostly happier. And then there are a bunch of nations that are much richer, and yet they don't seem to be happier. So if you include all the red squares with the blue dots, it turns out you probably really don't want to try to fit a straight line through this anyway. This is more complicated than being a straight line. And so your sample here was not really representative enough. Didn't really describe the universe of of the real world out there as much as you might hope. All right, and then there's poor quality data. Whenever you get data, there's usually limitations and errors in it. So you spend a considerable time cleaning it up, fixing errors, removing the outlying points, figuring out, dealing with things that are missing some of the data, like some of them don't specify their age of your customers. Then you can either ignore that entirely, or you can have one model that includes age and one that doesn't include age, but you have to cope with these problems. Then there's irrelevant features. You're talking about before, a data science term for this. Feature engineering is one term for this, where you're choosing what features to train on. So you select the best features from the available features, or you extract new features by combining features, trying to figure out what of the available measurements are most useful to train your model on. And then there's overfitting. If you have data like this, the GDP per capita, you could fit like a high-ordered polynomial to it, and it will do this. It goes way under, way over, way under, but it passes right through most of the dots. Mathematically, this has a smaller error, but in practice, it's obviously a ridiculous curve that is not going to represent it. This, by the way, is what happened to Donald Trump. In the early days of the COVID pandemic, Donald Trump came on TV and he said, COVID will be completely over by Easter of the first year it came out. He said that with incredible confidence. And the reason he said it is because one of the people that worked for him was a financial analyst. And they took the medical data, which is how many COVID cases there have been week by week, and they put it in Excel, and they fit a fourth order polynomial to it. And that showed it going up and coming down and hitting zero in 1 month. It was a prediction like this. It was overfitted prediction to the noise in the data. Just lost me? Can't hear me anymore or what? I hear a statement. Did the sound cut out? I see. Last thing is a thing saying just lost me. No, you good? I can hear. Oh, good. Thank you for telling me. Okay, good. All right. So good. So maybe one person. Okay, good. All right. And then nothing. Lost you. This is what happened to Donald Trump. Okay. Well, people can hear me apparently, Karen. Anyway, what happened is they had data showing how many COVID cases there were per week, and they fit a high order. Yeah. Lost your sound? Try refreshing. Twitch. Apparently it's still working. Yep, good. All right. And that's what happened. This kind of overfitting, like right here you can say, well, apparently at a GDP of 75,000, people are just miserable. You could predict that from this data, from this curve, if you believed it, but of course it's just a stupid curve. Anyway, so that's the thing to know. So regularization is the task of making a model simpler to reduce the risk of overfitting. So what you do in this case is you would not allow it to fit a high order parameter. This looks like maybe an 8th order polynomial here. You'd say, no, you have to fit something no more complicated than maybe 3 or 4 parameters here. That's regularization, where you force it to use a simpler model, even though that is not going to have the lowest error, but it's probably going to have the most generalization to the real data. All right, and so you do that with a hyperparameter. A hyperparameter controls the amount of regularization, and so here you have an example fitting on just the blue dots. The linear model on partial data gave us this steep curve, but they added regularization. Here's the linear model on all data is the black curve, and the regularized model on the partial data is closer because they took a regularization parameter, a hyperparameter, and said, we're going to not let the slope get too high. Even though a steeper slope would fit the existing data, I don't believe that. We're going to force it to use a lower slope, which is probably more representative of the real data. So that we'll do more of that as we go ahead. These things are called hyperparameters because they are not adjusted in the course of learning. They're imposed by the designer to limit the available variations allowed to the model to learn in order to prevent it from going into a crazy space where it fits the training data too well, but no longer matches the real sample, the real universe of samples available. Now, underfitting is when the model is too simple and doesn't learn the underlying structure. So, for example, if we were to try to fit a straight line through all this data, you can see it, argue it's underfitting. Anyway, that's another possibility. With your training data, you failed to learn the information that was present in the training data. So you need an even more powerful model. You might need to choose better features. You might need to reduce your constraints so it has more options. All right. So just a summary. Machine learning is about making machines that get better at a task by learning from the data instead of having humans write rules. And so there's supervised and unsupervised learning. There's batch and online learning. There's instance-based and model-based learning. So you have a training set of data that the model learns on, and they feed that to a learning algorithm. It then tunes some parameters to optimize the model if it's model-based. If it's instance-based, it just learns the examples and generalizes to new instances by using a similarity measure. It will not perform well if your training set is too small, or if the data is not representative, or if it's noisy or has garbage features in it. And your model needs to be not too simple or not too complex. And this is human judgment. You know, it's not a You have to put in a considerable amount of intelligence and human analysis to get a good job here. It's not like the machine does everything. Humans have to massage the data and set it up to make it easy for the model. So then you want to test your model, see how good it is. In the first place, how important is the integrity of the data in creating, well, it has to be accurate enough. You know, like if your model has errors, it won't matter unless it has too many errors. So that's why there's no simple answer. You know, if the data has some parts of it that are wrong, the question is, are those the parts that matter? Can you easily find the wrong parts and remove them? There's no simple answer. So you got to split your data into a training set and a test set. You train on the training set, and then you test the result on a test set to see how good it is. So the error rate on the test set is called the generalization error, the out-of-sample error. If the training error is low, but the generalization error is high, then you're overfitting the data. You're following the details of the training set, but you're not actually capturing the real trend in the actual test set. If you have regularization hyperparameter, then you're also going to have to take some of the data and make a validation set to select the best value for the hyperparameter. And another way to do this, which is considered better, is cross-validation, where you use many different validation sets and you get a more accurate hyperparameter value. And we'll do this later on in the projects, where you do something like split the data into 3 pieces, train on 2 pieces and test on a third, and then train on the other 2 pieces and test on this third. You do the whole thing 3 times, mixing which part you train on and which part you test on. That's called cross-validation. It means more time and more calculation, but it's considered a more accurate way to choose good parameters. And then there's data mismatch. So it looks like you need an N here. So you want to train an iPhone app to recognize flowers. Recognize. So it looks, anyway. So you could download flower photos from the web, but they weren't really taken with an iPhone. So they're not exactly the same as the real case. So now you have a training set and a test set that are not really the same. So make sure, and if you have to do this, make sure that the validation and the test set are real representative samples. So even if you find something else to train on, what you want to know is how accurate is it on the real data that the real app is going to use. All right, so let's try another Kahoot, which should be here, and so it is. Yeah, I see the discussion that Jordan's got there. It depends, on what your data's like, what you're trying to predict, and all that. There's not going to be any kind of simple answer. The question is, how important is the integrity of the data? And, well, no simple answer. All right, let's try it. All right, so the system memorizes each image and compares test systems to see how similar they are to them. That should be test images. That is instance-based. where it just memorizes the training data. All right, which one is best to stay up to date with changing data? All right, that's called 9 training. Good. All right, so which number increases as the model gets better? That's the utility function. All right. All right, and which of these lowers generalization error? All right, and that's the hyperparameter is used to push your model in the direction of the real population, even if your training data is not fully representative of that. All right. All right, Kate's won twice, and Woot's won twice. Okay, good. I've got the winners. Let me see if I can figure out how to stop the recording.